What's happening, y'all? Welcome back. In this video, we're going to talk about an example that we saw in lesson 17. Specifically, we're looking at this general linear systems problem that involves a 3 by 5 matrix given, a 3 by 1 right-hand side vector given, and an unknown vector x, where we want to find the scalars entries of x to multiply against the individual columns of A to produce this in that linear combination. We recall from our last video that the complete solution to this linear system takes the form of the template, a particular solution, plus a solution that gets sent to 0 by my matrix. In this video, we're going to use this example to study how to generate both the particular and trivial solutions using information in the matrix A. Before we do that, let's go back to the structure that we're using to solve general linear systems. It's the same thing that we did in non-singular linear systems, as we talked about in lesson 17. We start with the original problem. We multiply that problem on the left by a sequence of elementary transformations, elementary matrices, shear matrices, dilation matrices, permutation matrices, to get this thing in special form. The special form we're shooting for is reduced row echelon form, because that reduced row echelon form is going to give us very, very clear intuition on what the particular solution is going to look like and what the zero solutions are going to look like. If you look back at your notes from lesson 17, you're going to see that we already translated this general linear systems problems into the equivalent special form of the linear system problem by multiplying both the left and right-hand side of this equation by elementary matrices. However, one of the themes in my class is I don't want you to trust me. So what I'm going to do is actually show how to do this quickly for free online. Let's go to Octave Online. I don't need them to tell me how to work with this. I'm going to go ahead and clear the entire screen, which is CLC. I'm also going to clear memory, which is kind of unnecessary. Let's go ahead and define A. A is going to be the matrix -3, 6, -1, 1, -7. Semicolon gets me down to the next row. Row 2 is going to be 1. Next column is going to be -2, 2, 3, -1, semicolon drops me down to the next row, 2, -4, 5, 8, -4, and that should be the matrix A. Let's go ahead and confirm that the matrix A is what I'm expecting. Yeah, when you're coding, it's worth spending a little extra time to make sure you didn't make a stupid mistake, because this is going to save us a ton of time in the long run. The right-hand side vector is B equals -13. Next row down is 6, semicolon, next row down is 13. Now what I want to do is turn this into rref form. We could do that by sequence of transformations, but check this out. Now the problem, do you see that? I actually get the exact rref form that we calculated using our sequence of transformation by using the function rref. I also have a video which I'll post in this playlist about how to do this on a TI calculator. We get the exact same matrix out, but the problem is, notice that this rref form only does the transformation to the matrix A. It leaves the vector B untouched, but that's not how this works. If I multiply the left-hand side of the equation, I should also multiply the right-hand side of the equation. So what I'm going to do is I'm going to start this thing called temp. Temp is going to be a matrix which is formed by taking the reduced row echelon of what we call the augmented matrix, which is the matrix A, and then I just literally tag on the next vector right next to that, which is B. And then what I want to do is take the last row of temp. So temp, let's see, this is going to be the last column, I'm sorry, so this has 6 columns. So now I have U is my rref matrix, and then Y is my right-hand side vector, which is exactly what we see here. That's how we use a calculator to do that. Now that we translated our original linear system into the special form ux equal y, the real question is, how can we use information about the reduced row echelon form, the stair-step structure of that thing, to find both the particular solution and trivial solutions that get sent to 0 under this map, looking at that matrix? Before we answer that question, I want to introduce some terminology in a non-formal way. If we look at the reduced row echelon form of our matrix, this has 3 rows and 5 columns because rref always has the same number of rows and columns as the original matrix. The columns where there's a single non-zero entry that is equal to 1 in the leading position, we're going to call those pivot columns. So just look at those things in front. So there's a 1 right there. That's going to be pivot column 1. And then this one right there, that's going to be pivot column 2. All the columns where those entries do not show up, we're going to call non-pivot columns. We have a total of 5 columns. There are 1, 2 pivot columns highlighted in blue. And yes, blue means there's something to do with the particular solution. 5 minus 2 is 3. We must have a total of 3 non-pivot columns. The whole idea here is I'm going to be looking for solutions of my original system by searching an equivalent system in special form. We're starting with a particular solution. Let's go ahead and look at if I have u unknown x equal to 4, 1, 0, what values can I put in the first, second, third, fourth, and fifth entry to force those columns to 4, 1? Well, check this out. I know that 4, 1 is going to be 4, 0, 0 plus 0, 1, 0, which is 4 times pivot column 1 plus 1 times pivot column 2. Another way to say that is I need 4 of the first column, 0 of the second non-pivot column, 1 of the second pivot column, and then none of the other non-pivot columns, which is a really clever way of saying the number of pivot columns are actually hidden in this right-hand side vector here. So I needed 4 of the first pivot column, 1 of the second pivot column. There is no third pivot column, or another way to say that is the third row is all 0, so I'm not tripping on that one. And then in the particular solution, to make this real easy, we're not going to include any copies of any of the other columns. For those of you that did not take my class, go back and watch my introduction to matrix vector multiplication by taking linear combinations of the columns of a matrix. That's one of the 3 paradigms of matrix multiplication that we study heavily in this class, and I've posted YouTube videos to introduce that formally. Let's quickly use Octave to confirm this. P equals, we had 4, next row was 0, next row was 1, and the last 2 rows were both 0. And then let's go ahead and check u times p. Indeed, that's equal to y. 4, 1, 1. Because the whole idea is I did this. Now, this is where I'm going to blow your mind and kind of set up the next videos. Actually, not only is u times p equal to 0, but also a times p is equal to b. If I get a particular solution to the special system ux equal y, I also get a particular solution to the original ax equal b system. That is amazing, isn't it? Now that we've confirmed this in Octave, let's go on to find the vectors that get sent to 0 under the map A. We've just seen that using the rref structure, we can get a particular solution to this equivalent problem, focusing on the pivot positions. What if we now want to transfer over to another problem, which is how do we get vectors that send the matrix U to 0? Once again, before we dive in, I want to introduce some terminology non-formally. We'll do definitions later in this lesson. We're going to call R a non-negative integer, which represents the number of pivot columns in the matrix U. In this situation, we immediately see that R is 2, since I have 1, 2 pivot columns. We're going to say that F, for free variables, F represents the number of non-pivot columns in U. In this case, I have 1, 2, 3 non-pivot columns, so F is equal to 3. Notice the rref structure of this matrix makes it very, very clear. Each column of the entire matrix is either a pivot column, exclusive, or a non-pivot column. It can't be both a pivot or non-pivot. It's either pivot or non-pivot. Since the number of columns of our original matrix A equals the number of columns of our special form matrix U in rref, we know that the number of columns has to be equal to the number of pivot columns plus the number of non-pivot columns. In standard mathematics, that means 5 equals 2 plus 3. Moreover, in order to find the general trivial solution, the complete trivial solution to the AX equals 0 problem, to the homogeneous linear system, we're going to use the following observation. Each of the non-pivot columns can be written as a linear combination of the previous pivot columns. Another way to say that in normal language would be, hey, column 2 is a linear combination of column 1, or column 2 is linearly dependent on column 1. Similarly, hey, column 4 is linearly dependent on columns 3 and 1. Or non-pivot column 2 can be written as a linear combination of the previous pivot columns, pivot column 1 and 2. The same is true about non-pivot column 3. Each of the non-pivot columns encodes linear dependencies amongst the previous columns of that matrix. That's the benefit of that stair-step structure. The claim we're making in this example is if I want to know about how to find trivial solutions, I should study the linear dependence relationships between the non-pivot columns and previous pivot columns. Let's go ahead and remind ourselves the colon notation for columns. This comes from MATLAB, and Octave uses the same information. If you want to see more about that, please go back and watch my previous videos. The first thing we're going to do to get a sense of how to find these 0 solutions, the things that get sent to 0 under our map, is to look at the first non-pivot column. So if I look at non-pivot column 1, which is the second column of this matrix, that is -2, 0, 0 in a 3 by 1 vector, well, that's going to be -2 times 1, 0, 0. But notice that 1, 0, 0, that's pivot column 1, which means my second column of this matrix is written as a linear combination of the first column. It's written as column 2 equals -2 times column 1. Or 1 times column 2 equals -2 times column 1. Remember in algebra, if I have an equation and I want the right-hand side equal to 0, I can bring one or the other quantity onto the other side. In this case, why don't we add 2 of this column over to the other side? The 2 becomes positive, the 1 stays positive, so now I have 2 times column 1 plus 1 times column 2 is equal to 0. You might ask, why do I want 0 on the other side? Because that's the definition of a trivial solution. It sends the matrix to 0. I want one side of my equation to be equal to 0. This vector equation has this realization when written in terms of the individual elements. And the question that we ask ourselves is, can we get a special solution using this information? Well, yes, we can. Here I need 2 copies of column 1, 1 copy of column 2, and notice that none of the other columns show up in this linear combination, so I'll take 0 of column 3, 0 of column 4, and 0 of column 5, which means I have this first special solution to the u times z equals 0 that comes from studying the linear dependence between the first non-pivot and the previous pivot. Let's go ahead and confirm using a calculator. We just said that z1 was going to be 2, next row 1, last 3 rows were all 0. And then we're going to say u times z1, indeed that is 0. In fact, a times z1 is also 0. Finding the trivial solution for the special matrix U is equivalent to finding the trivial solution for the matrix A from our original problem. We've made this claim that to find trivial solutions, we're just going to study non-pivot columns. We just finished studying the first one. Let's go on to the second non-pivot column. We see that the fourth column of our matrix, which is -1, 2, 0 as a 3 by 1 column vector, is equal to -1, 0, 0 plus 0, 2, 0, both column vectors. But that linear combination, we see with the stair-step structure, hey, these 2 entries map back to the original pivot columns. In other words, I can decompose my fourth column as a linear combinations of columns 1 and 3. -1, 2, 0 equals -1 times 1, 0, 0 plus 2 times 0, 1, 0. Non-pivot column 2 is a linear combination of pivot column 1 and pivot column 2, looking backwards. Using colon notation, I see that 1 times column 4 of my matrix is going to be -1 times column 1 plus 2 times column 3. Remember, we're trying to get the right-hand side equal to 0, so we can either bring the left over on this side or the right over on the other side. doesn't really matter. In this case, I'm going to keep the scalar in front of the fourth column to be positive. 1 comes over and it turns to positive. So now I've got 1 times column 1 minus 2 times column 3, because the positive comes negative when it comes on the left-hand side, plus 1 times column 4 equal to 0. We again ask ourselves this really beautiful question, hey, can we get information about how to send our matrix to 0 from the linear dependence relationship between these columns? And yes, we can. That's why we studied matrix multiplication as linear combinations of the columns. In this case, I'm going to need 1 times the first column. The second column does not show up in that multiplication. The third column shows up with a scalar of -2. The fourth column shows up with a scalar of 1. And the fifth column is not there, which means that for my second non-pivot column, I get this special solution, 1, 0, -2, 1, 0. Similarly, we can check that the vector z2, which was 1, 0, -2, 1, 0, when I multiply u times z2, I get 0. If I multiply a times z2, I also get 0. That's the benefit of the matrix U. You astute viewers out there might be thinking to yourself, well, how many of these special solutions do we expect? Of course, we said that the number of columns is equal to the number of pivots plus the number of non-pivots. We have done 2 non-pivots. We expect 3 total because each non-pivot column generates its own special solution. With that in mind, we're going to look at the last non-pivot column, and we're going to say, given this stair-step structure, I can write the last column of my matrix as a linear combination of the previous pivot columns, or columns 1 and 3. In order to do that, I see that the last column, the fifth column of my matrix, or the third non-pivot column, is going to be a 3x1 column vector, 3, -2, 0. And we can write that as a linear combination of the 3, 0, 0 column vector plus the 0, -2, 0 column vector. But we can decompose that non-pivot column as a linear combination of our pivot columns by multiplying the first pivot by 3 and the second pivot column by -2. This leads to the representation that 1 times the fifth column of my matrix is going to be 3 times the first column plus -2 times the third column. The whole point of this was to generate 0 solutions that get sent to 0 under my matrix. One of these sides we're going to set to 0. In this case, I'm going to bring the right-hand side over to the left. The positive turns to negative, the negative turns to positive, and I get -3 times column 1 plus 2 times column 3 plus 1 times column 5 gets sent to 0. This is the third time that we've seen this type of work. Question, given this linear combination getting sent to 0, is there a way to generate a special trivial solution towards the associated linear systems problem? And of course, yes, there is. -3 times the first column, none of the second column, 2 of the third column, none of the fourth column, and 1 of the fifth column. And all of a sudden, we have 3 special solutions and 1 particular solution. Once again, we're going to check that the vector z3, which was -3, 0, 2, 0, 1, when I multiply u times that vector, I get 0. Now, when you see that e to the -16, that's like -4.44 times 10 to the -16. That's the numerical equivalent of 0. So you got to interpret that. But the claim is, if we know that z3 sends u to 0, z3 also sends a to 0. And that's what we're seeing in that case. What have we just done? We've constructed every solution to the ux equal y problem as a particular solution plus special forms of 0 solutions. And we're going to make the claim that any linear combination of those original vectors z1, z2, and z3 that showed how to take the columns of u and send them to 0 actually also sends the matrix to 0. We will formally develop this theory as the lesson goes on, but the whole idea is when we multiply u inside this sum, we can distribute u to the p and then distribute u individually to each of the scalar multiples times each z. So that's literally just distribution. And then we know by homogeneity, the whole idea that I can bring out each of the scalars, I get u times p. A particular solution means that I get sent to the original y. That was the definition of the particular solution. C1 times u times z, the C1 came out, the C2 came out, the C3 came out, but what was the whole construction of each z? Each z sent u to 0. Encoded in each of these vectors was the idea that we're going to take linear combinations of the columns and uniquely get sent to 0. That's how the construction worked. Well, we know that any constant times 0 is 0, so now I get y plus 0. That's the reason that the template took the form that it did. But y plus 0 is y, which means this general template solves that linear systems problem. And this is why elementary matrices and invertibility is so powerful. I'm going to make a claim. Solving this problem actually gives a solution to the original problem. The equivalent special form gives us deep insights into what happened with our original matrix. Specifically, if I want to know the complete solution set, I'm going to write every vector in the solution as a particular solution plus a linear combination of the special trivial solutions that came from looking at the non-pivot columns of my matrix. Or in other words, if I want to know every single possible vector that solves this problem, I can write that entire set in this form. We'll confirm this in a future video, and we'll actually answer the much more important question, which is, why does this work so well? How is it possible that just translating things into rref form using elementary matrices solves this problem? In the next video, we'll get some insights. I'll see you in the next video.